So again, hello everyone and welcome to performance testing webinar. This is my last webinar for this year. It's time for the Christmas holidays already. And I thought it would be interesting to end the year with something very much about testing, very deep in the software quality. Performance testing is a huge topic. I've done some, not very traditional one, and I also had to prepare for this webinar. I've never done so thorough research recently in the last couple of years to come up with very, not really high level, but actually very straight to the point guidelines or recommendations or a list of resources you'll see about performance testing. It's a huge topic, and there are some misunderstandings, or I believe it's not thoroughly understood. So today I've tried to assemble something useful. As little or as little percentage of the companies out there are doing testing at all. Even fewer do performance testing. It's either we wait for enough user base, or we wait for our revenue to grow, or we're very much in a hurry to release our MVP, to go to market, to really build the functionality. So performance is something, and there is an understanding that you need to have a ready product, something ready, something working already on production in order to define your performance requirement or to start testing at all. This type of thinking has led many teams into fixing production and performance issues at New Year's Eve. We don't want this to happen. Performance issues are one of the most tricky, one of the most difficult to investigate. They definitely need time and actual money because performance tools most of them are pretty expensive. So there's more approaches to this. Let's see, I'm sharing my presentation now and moving the Zoom screen to another one, so you'll see my profile. Share screen. No, spoiler. All right. So performance testing and why it's never too early to start. My name is Christina. Welcome, someone. Unless you have a question. If you have a question, you can unmute anytime, stop me, interrupt me. I would love to just discuss anything you need during the presentation or save some for the end. It's up to your preferences. So my name is Christina Koleva. Apparently, who am I? I've been doing testing and QA for more than 16 years now, various products, various technologies, all sorts of tests, all phases of the software development lifecycle. I dare to say I understand what software quality is. All these years, I've tried to figure out how many bugs I've reported, and I've approximated them to 5,000, but there are more actually. And all these years, I've learned that testing is not enough to ensure the quality of the software. We need quality assurance. We need discipline and conscious activities throughout the entire software development lifecycle, and need a process approach. If the way we work is not efficient and not effective, we can't expect high quality at the end of that process. So I'm a lot about process improvement recently as well. My focus is on helping startups find their way to software testing and quality, because as I said, there's so many, the majority of software companies don't have any testing processes in place. They just go for it. If it works, if nobody complains, then we're good. If somebody complains, we'll fix it. It can work, but you need very high-skilled teams to do that. Most aren't. So this is my focus, and I'm kind of a rock fan, a Liverpool fan also. So if anyone's interested, we can chat about this as well. Today's topic, what is performance actually? What are the performance capabilities? What are the different types of performance testing? Most of you probably are familiar with this, but we need to start to set the ground from somewhere. Typical performance issues. Also, I'm sure these are things most of you have dealt with, but it's good to have them at one place. And a couple of practices I found very interesting to prevent performance issues. A little spoiler, you start from the beginning. You start thinking about performance from the beginning of your development, not when it's ready, but this is applicable to all the testing. So it happens after change, after major release, after a new pull request merged to the repository or uploaded to the test environment. We hear some of our colleagues online, if we're remote or at the office, do you have internet? Why it's so slow today? And I think we all love the sentence we've all heard so many times, it's not working. Very often it is working, but something is not sufficient. Some resource is not there for us. A huge, and this is straight to the point now, a huge misunderstanding about functional and non-functional requirements. You'll see a little bit later, functional requirements are 10%, this little portion of what we need to deliver. The what from the requirements is this little. It's not all. And we're all focused on the what. What needs to be delivered? What functionality? What value for the users? The what, the what, the what. Nobody thinks about the how or the non-functional requirements until something really breaks. And this picture is brilliant. For me, this is what we do. Usually, this is how we describe. How many of you, please tell me in the chat, let me open the chat. How many of you have ever worked with product requirement document or user story or a ticket or whatever type of requirements items you use, a task? How many of you have seen non-functional requirements written by the product managers? Meaningful non-functional requirements. Please share in the chat. Let's see. I'll give you a minute. Who have seen non-functional requirements? Come on, people. Someone, anyone, please. Or you can unmute yourself and share.
No one.
No one. I'm trying to open the chat and the gallery to see how many people we are here right now. It's amazing, right? No one. No one, and it's not a paradox. It's not a ridicule. I don't know what it is. We don't build these these features or this software for ourselves. We built it so it's used by someone else. And usually, and nowadays, most of us build software that we want to be used by as many users as possible. We want thousands of users, hundreds of thousands of users. Then how is it possible that we don't, it's like we don't believe we're getting there. I will build it now. There will be 10 users, who cares? It will work. It works on my machine. It's like we don't believe we can get there. We can get tens of thousands of users. That's why nobody thinks about performance requirements. First lesson for today. If there are testers in the audience, demand non-functional requirements. If there are product managers in the audience, believe you will get tens of thousands of users, and imagine how your system will behave when they start using it at the same time. When you launch a marketing campaign and you want tens of thousands of, it was Black Friday recently. We're all using these products every day, these softwares and systems where they handle hundreds of thousands of users. Why don't we believe our software can do this? Start thinking about the performance as soon as you think about the functional requirements. Immediately, right there. It should be part of your product requirements definition or the description of your ticket. It should be there. What do we want to build? How do we expect it will behave under these and these performance conditions? Here. So here I'm going even further. Even before elaborating on the what, start detailing the how. Because we get derailed into refinements, into UI, into mockups and UX, into the architectural design and the technical solution. We get derailed, we get immersed, it's fun, we can see it, we can touch it, while the performance is something on the side. We don't really feel it, it's not tangible. We can't imagine, we can't build it. Yes, but we can actually, and if we define it early, we will be able to account for it early. Typical performance issues. These are the typical performance issues. Most of the performance issues are due to these, and there are many more. I have picked the ones that I have any experience with. And I have even duplicated the configurations issue, because let's look into those. Subpar configurations, insufficient configurations, it's pretty much the same book in the presentation. The thing is that it's a huge problem nowadays, especially when we talk about cloud solutions. Cloud made us a little lazy about performance, because if we need resources, we just pay for them, and that's it. There is an actual belief in some engineers that we don't really need to optimize so much for resources because hardware is cheap already. And especially with cloud, it's even more accessible. You don't need to think about it. You just click a button and enhance your resources. It's not very true, of course. It's delusional. And it's even more delusional when you don't understand how your cloud configuration works. And that, for example, Amazon can just shut down a server of yours because they're doing maintenance. And if you don't have proper configuration, if you don't know how they're configured, if you don't know how to set up your cloud infrastructure, you will suffer. Two examples. One, a bug causing huge retries of failed jobs. And all these retries were bringing more resources. And this bug cost double, duplicated in the amount invoice from the cloud provider. If it was, I don't know, X amount of money per month, usually that month it was double because of a bug. Why? Because it was important for that company to have infrastructure. They were not short on expenses. They didn't put, it's called a price cap. They didn't put any limit on the pricing, on the spent amount in the cloud. So it was just using more resources and more resources and more resources and more resources. So for one day, they managed to double the monthly invoice. Another example, there was a price cap, but it was not sufficient. And usage grows, data grows, transaction grows. Suddenly, the server is not sufficient and it might get blocked. It will go down, because after all, you need those resources, but you need to use them smartly, and you need to manage them. You need to monitor them all the time. Bad index and bad query is typical problem. Those that are both are the ones that we've really all suffered from. Typical problem when we deal with databases. Unnecessary, excessive amount of requests and queries are typical problems. Unoptimized database operations. Not enough bandwidth. Not enough settings for the connection pool. We've all seen this. Performance degrades over time. And let's go back here. Performance degrades over time, and these start to slightly show up and emerge with the data grow and with the traffic grow of our system. At certain moments, 2 seconds could be kind of okay for something to load, but then it starts to become, in 1 year, there was, while I was doing the research, there was this nice analogy of the frog being boiled alive. It's one of the terrible tales out there, but it's very true. 2 seconds is fine, 3 seconds is fine, and then suddenly it becomes 30 seconds, and our customers are blocked. They spend so much time into performing a simple operation, but they can't really ditch us or can't stop using our product because they've been using it for years, for example. And then it becomes very difficult to solve such issues. Then you need to do something dramatic that is expensive, risky, and so forth and so forth. So pay attention, use this as a checklist. It's full of, I have a slide with links, with resources where it's full of suggestions what to pay attention to. It's not only about measuring time to load. There are plenty of components that can lead to work. Hello there. Who's there? Do you have any question? I heard someone, so I assume. Let me, all right, anyway. Again, if you have a question, unmute yourself, ask the question. If you don't have, mute yourself. So, what is performance? Performance efficiency, and that's the formal name of performance, capability, quality. and capability, there's a standard. ISO 25010 is the software product quality standard. This is where all the ELTs come from. Performance, usability, compatibility, reliability, maintainability, all of these come from the standard. And this is the only link I've missed. I suggest, if you don't know it, go there, read it. Oh, actually, I have another link that it's more useful. So the definition about performance efficiency. There are 3 subcategories: time behavior, resource utilization, and capacity. When we talk about performance, we want speed, pretty much. We want fast response time, or reasonable, or the one that's required for that particular operation. We want processing time to be short, usually, and we actually want high throughput rates. Then we want reasonable resource utilization. What are the resources? CPU, bandwidth, network bandwidth, memory, disk. These are the resources. And then, given the capacity, all these of these resources, we want the maximum limits to be sufficient. So these are the 3 subcategories. We'll go into more detail for each of them. However, when we talk about performance, you can't, or when we talk about quality, you can't just say it works, or only high performance is not achieved by only performance testing and focusing on performance testing. You can do a lot of performance testing and your system would still be slow and operating poorly if that system doesn't have other qualities. The other qualities are reliability, and with the most, the ones that are mostly related to performance are sub-qualities are availability, fault tolerance, and robustness. Because if you have low performance, your system will easily get to become not available. Oh, okay. Enable. Sorry, I have forgotten. Someone requested live transcription. I have forgotten to do that. So reliability is how reliable, how stable our software is over time. If we have low performance, it will become unreliable. And you know the typical, what's the typical performance attack? It's the denial of service. Denial of service is something so-called DOS attack. And DDoS attack, distributed denial of service, it's something, it's typical performance issue. It's not a security issue. It's typical performance issues because our system can't handle all these requests and all this traffic. It's not a security issue. And something very, very, very important is the data persistence. It's immediately related to performance. Of course, if we have low performance, the data will not be able to get retrieved with the amount of within reasonable time, within reasonable resources. And the majority of performance issues are because of poor data management. So something I will copy the link. Something for you to try is to understand non-functional qualities and to start using them early in your process is a quality map. This is a Miro template. Miro is a collaboration tool. Also try it, it's very popular. It's a quality map with all these quality characteristics that come from the standard, and also some additional ones that I've added from my experience and from other experts. So this is a quality map with all functional and non-functional qualities and their definition. This Miro board in particular is used for early identification of critical non-functional qualities. Start thinking about the non-functional qualities early, prioritize them in step 2, and then in step 3, identify tasks for the different roles in your team to implement, to make sure these qualities and these non-functional requirements are actually met. So within that template, there are a few examples. What I only wanted to show you is give it a try, look around, play with it. It's public. What I only wanted to show you is this. This functional suitability is the only functional quality out there. I have actually divided them the way I imagine. This is not in the standard what is functional and what is non-functional. All of these are part of the standard, together with the data quality, which is also, as we saw, directly related to performance. But as you see, only this yellow box is what we usually focus on. We usually focus on the what. The rest, and the rest are 52 non-functional qualities that affect not only performance, but all of them affect performance. And poor performance affects all of them. So give it a try. I hope it's going to be useful for you. So after that, to summarize, again, performance degrades over time because data and traffic grow. You don't need to wait for the data and traffic to grow unmanageably, to grow to levels that you didn't believe it will get to start thinking about whether your system will be able to handle them. You need to start identifying what are the levels of performance you want to deliver to your users, imagining sustainable growth or irregular growth or peaks into the traffic, peaks in the traffic, imagine them, plan for them, start testing. What are the type of performance tests? This is from, these definitions are actually from ISTQB. Some of you are familiar with it. It's an International Software Testing Qualification Board. They have syllabus for performance tester. It's very straightforward. I actually recommend it as a resource, the syllabus, not the certification, but I recommend the syllabus because it has it all. It's very thorough and it very well defines and describes what is performance testing. So as you see, performance testing is not only about measuring how quickly our page opens and how quick our data loads. There are different types of performance tests. The type is determined by the goal of the test. What is the goal of that test? What do we want to verify with that test? Is it increasing levels of realistic load? Is it the ability of the system? What is the load testing? Is it the ability of the system to handle peak loads? Which is the stress testing? But then also not only peak loads, but also reduced resource availability? Is it to respond to sudden burst of peak loads and then be able to recover when that load goes down, which is the spike testing? Is it scalability? Something very interesting, and it's highly related to the maintainability quality characteristics. Why? Scalability is an assessment of your system to identify if it will keep or increase its performance when you add more resources to it. And when we talked about the cloud infrastructures, you can add as many resources. Probably you can add as many resources as you like, but will it actually increase the performance? No, if your system is not highly maintainable as well, because maintainability is also about a system that is scalable, a system that is modular, a system that is easy to enhance, that can actually benefit from distributed resources and from adding more resources. So again, performance is not a quality that you can improve by itself without actually improving the quality of the entire system and the different types of quality. So scalability is very important when you consider your architecture, because if your architecture is not scalable, then whatever resources you add to the system, it will not be able to increase its performance. Endurance, the stability of the system over time, is a very interesting quality, or very interesting performance test. A small personal story here. One of my favorite projects I've worked with was a ship simulator. And it simulated maritime operations real time, like a game, but real time, meaning that you have a ship or a vessel, a boat, and you want to navigate it through the Panama Channel, for example. Someone mute themselves again, unless you have a question. You would like to start the engines of the vessel and navigate through the Panama Channel, and you have a timer that counts real time, that counts seconds. So that timer was our primary source of performance indicators, was our primary performance indicator, because that timer had to go real time. 1 second in simulation should have been 1 second in real time. So it was a very complex system, and we did plenty of performance tests there. But what about endurance? When I joined that project, it couldn't run for more than 45 minutes. It used to crash really it was a Windows-based system, so we were seeing that. Sorry for inconvenience, that component crashed. Sorry for inconvenience. We've seen all of this at desktop systems. Probably some of you haven't, because desktop systems are not so popular anymore. But we would observe that message every 40-45 minutes. So the system was not stable over time. Part of it, again, a lot of data, a lot of complex simulations, very complicated operations, high load, high CPU operations. It was processing. It was very, very interesting project. Then the requirements for the endurance were 12 hours. So the system was supposed to maintain real-time simulation for 12 straight hours without any issues. That was a particular requirement. So this is just a small example of endurance. What endurance would be for For every other systems, it's very popular with the infrastructure, actually, again, with cloud operations. You know that mission critical software have the 9 nines or 6 nines or 8 nines availability time, meaning that 99.9999 etc. % of the time the system would be up. And this is what mission critical infrastructures are selling. Actually, it's one of their selling points, that if you use our infrastructure, your system will have barely any downtime. There will be no downtime for your system. So availability, endurance, all of this, and they are supposed to also meet stress and spike requirements. All right, again, performance efficiency is how we use our given resources to perform particular amount of jobs. Resource utilization versus work done within those resources. Can we do our required amount of work given this amount of resources? Do we use those resources smart so that we don't exceed, there's no excessive usage, or the resources are enough, or if they're not enough, we actually have a smart way to increase the resources and get more work done within those resources. Performance is nothing but what we pay for and what we get done for the price we pay. It's to oversimplify it, it's typical investment resource versus gain, work done, amount of operations, users. So how much CPU, memory, disk, bandwidth, time we invest, we use to achieve or to support how many users, transactions, calculations, operations of any sort, records, requests. How much resources versus how many jobs. This is what is performance efficiency. This is what we want to evaluate. The different tools have various views, perspectives, slicing the metrics in various ways. So I have not gone into number of transactions or throughput or number of requests, etc. All of these particular performance metrics, because they're presented differently with the different tools, and the different softwares have different requirements for which metrics are important. But the primal principle is how much resources you will use to achieve the required amount of work of any type. Something very, very important for our performance test. And that has been #1 problem and challenge with performance testing. The test setup must be realistic. Typical problem. We either test on a clean environment with not enough load on it, not well warmed up environment, or we test on an environment that is too polluted, something shared environment with other teams, with other products, not realistic test environment. What realistic again means for your product is specific, but it would mean imagining how the system will, imagining your goals in 1 year. If in 1 year you want 20,000 users daily, then test for 20,000 users daily, simulate 20,000 users daily. Don't test with 1,000, which is today. There's also something very important. When we start identifying the performance test strategy, there are also 2 steps. The second one is what I just called. Imagine your future growth. The first step is actually identifying your bottlenecks today. So, steps to start your performance test strategy. Draw your architecture. Your architecture and / infrastructure is what is the preconditions for your performance successes and performance bottlenecks. You need to understand your architecture. You need to understand it actually at high level, at low, and at low level. You need to understand what each component is responsible for, how they talk to each other, where are simple example, 2 components, they talk to each other through some sort of API. This API has limits. You can be able to send 10 requests per minute, you can be able, or per second, you can be able to send 1,000. What are the needs? What are the bottlenecks? Or is this conversation a bottleneck? Could it become? Why? To be aware of this, you need to draw your architecture, and you can't imagine how few teams have living, well-maintained architecture documents somewhere, or drawings or diagrams. Almost nobody. Again, I could ask you, how many of you have seen the architecture diagram of your software? That's question number 1. Come on. How many? How many have seen the architecture diagram? Come on, people, where are you? Anyone? There are 20 people, not the whole architecture. All right, something. Is it, I have seen. Is it up to date? That's question number 2. What you've seen, was it up to date? Was it the way your architecture was at that moment? No, for sure. No, for sure. It all starts, your entire testing strategy should start with drawing your architecture. And when you talk about performance, it's even more crucial. Understand your architecture. This is where most of your performance problems lie. And all your testing problems and quality problems typically. Then identify the critical infrastructure. Which are the components of your infrastructure that should be always up? Which are the components that handle most of the traffic, most of the load? Which are the components that are exposed to high risk, if they go down, you're down. You need to be aware of these hot points of your infrastructure. I had something in mind, but I forgot. When you identify these hot points, basically, and it's something I have entire whole webinar about this topic. You can find it on YouTube. What could go wrong? Think about what could go wrong with these critical infrastructure components and how you can overcome it. What if that component goes down? How quickly you could overcome it? How quickly you could fix it? How quickly you could replace it? What will happen? And that's a typical problem. I have seen this so many times. What will happen? It's ridiculous, but it still happens. Initially, what if you hear someone crying? That's my kids wanting attention. So I will not. I'll try to keep within time. If your system goes down, If that component goes down, how many? Yeah, well, what my example? What happens if your disk space runs out? It happens. There's not monitoring, and that's for critical. And between us, it's an example from a bank. They don't have adequate monitoring of their disk space, and their disk space twice a year, they run out of disk space. The system goes down. That's insane. So draw your architecture, identify your critical infrastructure, and then the easiest thing to start about performance is to start monitoring those most critical features, components, and infrastructure, and record how they behave. Keep a record. All cloud providers have brilliant tools, or well, some are more convenient, some are more tedious to work with, but all of the cloud providers have good tools, good monitoring tools. Use them. Again, many teams don't even know how to use those tools, and they pay for them, but they don't use them. Use your infrastructure. If you're not on the cloud, there are other tools, but start monitoring. Don't think about complicated performance scenarios, how to build load, how to generate virtual users, how to generate huge amount of data. Don't think about these complicated scenarios, because they're more difficult to come up with and to set up. Then they're more expensive. Just start monitoring. Conscious monitoring about the behavior and the health of your systems. Those most critical components, most critical features, most critical infrastructure. Then you will start, and some of you, I'm sure, are testers here. You know that if you start testing consciously, you will start finding problems. So start observing how the system behaves. Start collecting statistics about usage, about peaks in the day, about how the system behaves during the day. In that particular project I mentioned to you above, we would do also profiling, which is sort of dynamic performance testing. We would attach a profiler tool in debug mode to the system, and we will actually start tracing how each method performs, how each function actually performs, how much time it takes. That, and especially because we had unmanaged code. Unmanaged code is C and C++. Why it's unmanaged? Because you need to manually take care of memory allocation and memory management. So you need to, we use those profilers. There was, I think it is by JetBrains, one of the tools that we used. There was a .NET profiler. I might be confusing them because I haven't used them for a long time, but they're actual profilers of executable files to trace each method and their performance. And we had to distinguish between managed code C# and unmanaged code C++, and how they behave, how much resources they would take, where if there is a bottleneck in which it would actually lead you to the exact method that causes that bottleneck, that takes the most of the time. So start profiling and start monitoring your most critical features, component, and infrastructure. This is where you start this is how you start with performance testing, not with buying complicated tools and building complicated performance strategy. Start with observing. You will see problems, you will see optimization opportunities. Then establish the benchmarks and the thresholds. Establish that you don't have, that your system shouldn't go below these thresholds in terms of any of the metrics you're interested in. And if it goes below that threshold or above this threshold, then there should be an active alert somewhere to notify you that something's happening with your feature or with your infrastructure. And this is something very important. I'll tell you what's the most important thing about performance testing. The most, and monitoring and profiling and all of these care about performance and infrastructure and reliability. The most important thing is that whatever you start doing, you need to have a conscious routines in the team to actually take action when something happens. Because what do I mean with that? I mean that very often teams are establishing these monitoring, these health monitoring tools. They have Slack channels that notify them, and nobody is actually looking there. There are no active team rules or team routines or team policies. Who is looking when? There are no support mechanisms. There are no process in place to actually take care of the alerts when something is below or above the set benchmark or the set threshold. So if you do these 4 steps, which are my guide and my recommendation for you to start with performance testing, then the 5th step is to actually establish team process to take look daily, regularly, once every 2 hours into those metrics, alerts, alerting system, whatever it is, dashboards, whatever it is in place for your infrastructure. Because otherwise you will only be collecting them and you will again do nothing about it. All right, more practices in place. Something that I've been very, very fascinated with is the notion of continuous performance testing. So to go back a little, performance testing doesn't start after you've built your product and it's on production and you have 1,000 users already. It is already too late. Identifying your performance strategy and performance requirements start with the writing of the user story and the writing of the initial requirements. This is where you have to start thinking about performance and non-functional requirements. But then you do it continuously. Slack are famous for their continuous load testing. They have actually established a practice of continuous performance testing. Read about it, find it. They're using an environment and tool called koi ponds. Koi is that the fish koi. You have seen it, an orange, yellow, orange, white Japanese fish. And they have used that allegory of koi ponds to do performance and load testing. They basically have environment for each of their big customers and then continuously test their new changes and new builds against those environments. Don't get me wrong, I don't say that you have to have environments for all your customers. It really depends on your software setup, business, etc. But read about Slack continuous performance testing. Why? Because apparently it is possible to do performance testing continuously on every build, on every commit, or once per day, but do it continuously, because the reason of a performance issue, and what our first slide, to avoid the questions why it is so slow today, what it's not working, do you have internet? To avoid this question, you need to have a check about performance after every commit, or at least once per day, because your system evolves. Developers are building new stuff all the time. What is the guarantee that one particular bug that I also gave you the example will not cause excessive invoice next month? So continuous performance testing is the 6th step of my performance test strategy today. You don't have to do it once before release. You don't have to do it once before sprint. You have to have continuous performance checks. And another very interesting notion is that there are not too much materials about it, but some are doing performance unit tests. There's an actual argument about whether that's not kind of an oxymoron, because to do performance, you need more load, you need more realistic environment, while the unit test should be very straightforward, clear, small, etc. But again, you could actually test at very low levels for performance, and you don't need to exercise the entire system, even though basically performance testing is just like any other testing. You have the performance test pyramid as well. You can test, as I said, you can profile the behavior of your methods, and you can trace bottlenecks to a method. Then you can have performance bottlenecks at integration level. Then, of course, when you are exercising the entire system and you have external integrations, you will have different performance profile and different behavior. But what we usually do is to test at that higher level only. And that's not enough. And you need the lower levels as well if you want to perform continuous performance testing. Something also very interesting, and that's two very particular practices. Again, if we go back to the denial of service attack, the typical design pattern that will prevent you from handling with denial of service attack is the so-called throttling. Throttling, and if you actually search, that's a link I've forgotten to add to the presentation. I will send you the presentation if you like later. If you search for throttling and Microsoft and on their Azure documentation, they have great list of design patterns, and all of them are directly related, and they affect and they improve performance. So take a look there. But what is throttling? When it comes to API, is pretty much putting a limit on the number of API calls you could manage, you could respond to. If you are providing integrations, if you're a vendor that actually provides public APIs, and you want plenty of customers, naturally you would put a throttling mechanism to your public APIs, because very few infrastructures can handle endless or infinite number of calls at the same time. So you would say 100 requests per second or 1000 requests per second, etc., etc. For account, it depends. There are different mechanisms. Something that throttling is also used in gaming. When we are, in gaming, I don't want to use the example we shoot something, but we press a key very quickly all the time. Click, 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 click. They use throttling to cut that, like they don't catch every single click and perform the operation every single click, because you can shoot, for example, 10 times per second per 2 seconds, let's say, or I don't know how many, but you would be able to click faster So they actually cut and only perform every second click or every third click or every fifth click because you're clicking too fast. So that's also a throttling mechanism. But typically, if you don't want excessive traffic, you would put a limit to your resource and you will say, my resource would not handle more than this. And when you talk about reliability, there's a famous, and I'm getting more and more fascinated by this practice, the famous Netflix chaos monkey and the chaos engineering paradigm. What is this? It's about consciously introducing chaos to your system, which is primary stopping a resource. Let's stop that server. Put the firewall here. Limit the bandwidth there. Do something chaotic. Do something that it's not expected. Do something that can happen in real life. Again, when we think about what could go wrong, everything could go wrong. Even the unimaginable would go wrong. Do something intentionally to make sure your system will be able to handle it. So, and there's the Netflix Chaos Monkey is actually a tool to do that. And there's another famous tool called Gremlin. Gremlin is getting better and better into chaos engineering. So take a look. If you need high availability, highly reliable system, highly performance system, you would definitely consider some of these practices, especially the chaos engineering. All right. Because all of us, most of us, and it's very famous nowadays to build event-driven microservices. Here's a link. I will now go into more details. A very specific link how one company, what tools and what setup they used to test event-driven microservices. And because I know that you're very interested in what tools, what are the performance tools, but my talk today was more about how to approach and how to start and what is important about performance testing. So here's a list, a link somewhere, one of the one that I liked, with 50 performance tools. They're open source, paid, any sort of there should be at least. I didn't walk through all of them. So there's a link with 50 performance tools. And last but not least, is a very well curated, according to me, list of resources about performance testing, because most of the articles out there will tell you what I told you. Some of the things I told you, you need to look into traffic, you need to look into the response time, you need, they're the standard things, but to go beyond this, you need to actually start doing it. You need to actually start dealing with it. You need to start doing analysis, monitoring, and observe how your system behaves, and to understand where it's bottlenecks. The bottlenecks are usually due to technical debt, usually due to legacy code. So performance is not a single thing. We'll just fix that and we'll just add a server and it will start working 10 times faster. It's a complex problem, and it usually lies in the architecture and the quality of the code, quality of the queries to the database, etc., etc. So here's a list of verified resources that there's useful information there. All right. My last, contacts. This webinar and the previous ones have been recorded and they're uploaded to the YouTube channel Software Stories. Find me anywhere if you have any more questions. If you have a challenge in testing quality processes you want to share with someone, find me I'm available. I'm a highly available infrastructure right now. So we have plenty of resources to give you any advice or recommendation. So these are my contacts. I'll be happy to hear what you're testing right now, and if there's anything functional or non-functional that you're struggling with a little. And that's it for today. Time for questions. Thank you so much for staying all the time. I see very plenty of you actually stayed. I will stop the share, and it's time to do. Is there more to the question? No. Okay. Stop the share. And did I stop it? Yes. No. So tell me, what type of performance testing you do? What are you struggling with? What are you dealing with? Is there anything you would like to ask? Who's there? Who's still awake? Hello, anyone? Do you have any questions, or we're done? Okay, Erin, no questions, but it was really interesting webinar for them. Thank you so much. All right, if you don't have any questions, or not right now, find me in the contacts I've sent you. And this was the last for this year. Follow me on LinkedIn. I have scheduled for the next month, pretty much. Some more interesting things are coming. Thank you for your time. I hope it was useful, and I'll see you around. Bye.